This is the third lecture for Text Unit 5, which is our unit about heat and chemistry. This part is concerned with finding heats of reaction using Hess's law. To illustrate Hess's law or introduce you to Hess's law, let's consider the following pair of reactions. We could take a chunk of charcoal, beg your pardon, and react it with half a mole of O2 and produce a mole of carbon dioxide. By the way, in heat chemistry, we often see stoichiometric coefficients that are fractions, which don't appear anywhere else. The heat of reaction is negative 110.5 kilojoules. It's exothermic, what you expect for burning charcoal. The heat comes off. Notice that we don't have complete combustion. Complete combustion is to carbon dioxide. We could react the CO with another half a mole of O2 to produce CO2. And heat for that reaction is negative 283 kilojoules. So that's also a combustion reaction, releases heat. In fact, not too long ago, people actually used to burn CO for heat in some situations. If reaction 2 happened right after reaction 1, in other words, if a mole of CO got made and then that mole of CO got reacted, naturally the total heat released can be found by adding delta H for these two reactions together. Further, we could write the two reactions together, C plus 1 half O2 plus CO plus 1 half O2 goes to CO plus CO2. This is what we get by simply adding the reactions together. 1 and 2 have been added. This is all the stuff on the reactant side for the two processes, and all the stuff on the product side for the two processes. Notice CO is the same on both sides. So it's as if it does not do anything at all. In fact, since it's the same before and after, it can be removed from the reaction entirely, like so. And naturally, we have 2 half moles of oxygen. Those could be combined to one mole of oxygen. As I've said, since these are two consecutive processes, we just add up the heat for both, negative 393.5. What we have is the heat of reaction for C plus O2 goes to CO2. In general, Hess's law says the value for the heat of reaction is the same whether the reaction happens in one step or in multiple steps. In other words, the value of delta H that we found on the last slide of the presentation is the one correct value for delta H for going from C plus O2 to CO2. A corollary of Hess's law is that the delta H for 2A goes to 2B's is 2 times delta H for A goes to B. In other words, if you double the coefficients for a reaction, you double delta H, and etc. If you triple the coefficients for a reaction, that triples delta H. That makes sense. Burning 2 moles of water releases as much heat as burning 1 mole of water. It's also especially notable that delta H for A goes to B is the negative of delta H for B goes to A. In other words, if you make a reaction go in reverse, delta H goes from positive to negative. That makes sense. That's just the law of conservation of energy. And the law of conservation of energy is what Hess's law is really all about. Hess's law makes it possible to find heat of reaction in many cases. Here's an example. Suppose we want to find delta H for this reaction. CN2S goes to CS2. This time we're making CS2, not CO2. We have the following information. Delta H for C plus O2 is CO2. We just figured that out a second ago. Delta H is 393.5. We can find information on the combustion of sulfur. Sulfur plus oxygen combine to make SO2, and delta H is negative 296.1. Most combustion reactions with oxygen are exothermic reactions. Further, CS2 can then react with, we could find a reaction where CS2 reacts with 3O2 to make CO2 and 2SO2. And delta H is negative 1072 kilojoules. Alright. Now we can, imagine what order the reactions happen. But from a practical point of view, the thing to do is algebraically rearrange reactions 1, 2, and 3 to produce a reaction that, like in our first example, adds up to produce this reaction. Alright, now I'll let you consider that for a moment. Here is what we would do. First, reverse reaction 3. Alright, that reaction, written in reverse, as we've noted, changes the sign of delta H to positive. Then we could multiply reaction 2 by 2. That reaction is written here. Delta H, as we noted, is 2 times delta H for that reaction. So it has a value of negative 592.2. Alright, now what I like to do is number these reactions I've created. So I've inserted these numbers. I'm calling this reaction, we've written down number 4. And I'm calling this reaction number 5. And I have delta H's for number 4 and 5. Now again, what I am trying to do is produce a set of reactions that add up to the reaction we're interested in. This one, notably, is a reaction with CS2 on the right-hand side. And we know we need CS2 on the right-hand side. This one has 2S on the left-hand side, and we know we need sulfur on the left-hand side. I leave reaction 1 as it is. I still renumbered it though, call it reaction 6. This one has carbon on the left-hand side, and we know we need a mole of carbon on the left-hand side. Alright, so we add these 3 together. Here I have the list of all the reactants. Here I have the list of all the products that comes from combining everything on the reactant side and the product side. Remember now the reactions we're adding are 4, 5, and 6. And that produces this set of reactions. Or rather, this combined reaction, which has a combined weight of 386 kilojoules. Alright, now, if we remove everything that appears on both sides, because it's not involved in the reaction, it's there before and after, and therefore not involved. And that means we can delete CO2. Both sides have 2SO2. And I can remove the 2SO2. Now here we have 2O2 on the left, and an O2 on, and another O2 on the left. That's 3O2 on the left. And there are 3O2 on the right, beg your pardon. And when I remove those, I have the reaction we were interested in. C plus 2S goes to CS2. Which means that this combined delta H is delta H for the reaction that we're interested in. Alright. Let's have you try this one. Suppose we want delta H for this reaction, and we want to get it from these two reactions. Alright, now you attempt this. If you like, go back and look at the two examples previously in this lecture and study those. Attempt this and then move forward and see the presentation to see the correct solution. We rearrange the reactions to make reactions that add up to the one we want. Reverse reaction 1 and doubles it. This gives us 2 KCl on the right and multiplies delta H by -2. I'm sorry, it gives us 2 KCl on the left. Left, not right. And here is the resulting reaction, which, if you like, you can number as reaction 3. Reaction 2 can be left the same, except it can be numbered as reaction 4. Okay, so now I've written down reactions 3 and 4 and their values of delta H, the heats of reaction. Next step is to add together, and remember the things we're adding together are reactions 3 and 4. Alright, so here are everything on the reacted side, and here's everything on the product side. And when you remove waters and potassium hydroxides from both sides, because these occur on both sides and do not participate in the reaction, here's what you are left with, which is the desired reaction, and delta H is 407 minus 342.2, or 65.0 kilojoules. Alright. One more. Let's determine the heat of reaction for this reaction. C3H4 and 2H2 goes to C3H8, given this set of 3 reactions. Alright, and again, you can attempt this problem, and should attempt this problem before moving on and looking at the solution. First thing to do is reverse reaction 3, which you've noted I already number 4 in this case. And that produces C3H8 on the right, 3CO2 and 4H2O gives C3H8 and 5O2. And delta H becomes, for that reaction, becomes positive. I can leave reaction 2 as it is. That has C3H4 on the left. Even though I left it as it is, I'll renumber it number 5 anyway. So here's reaction number 5, and here's its delta H, same as number 2. I also leave reaction 1 as it is, even though I renumber it reaction 6, and it has the same delta H. So here are 3 reactions 4, 5, and 6. Now the next step will be to add these 3 together. Add the values of delta H, and we have to check the 3 reactions we add together to make sure that's the reaction we want. The sum of reactions 4, 5, 6 is shown here, which, after canceling everything that appears on both sides, leaves C3H4 and 2H2 and C3H8. The desired reaction. Add up all the delta H for 4, 5, and 6. Note that we followed the addition rule for the arithmetic in this case. Delta H is negative 293 kilojoules. Alright, this is the last example problem, and this is the end of the Hess's Law lecture for Unit 5.